Okay, so good morning to all of you. Friday early morning class. So if you will have this 8 o'clock class every day in the week, or
Someday.
coming in, please, Nayan.
So not every day, but yeah, few days. Like
Okay, okay, good. So anyway, so let's get started. Again, a quick recap of what we discussed. Last couple of classes, we discussed the concept of boundary conditions and why it is important. Because we are dealing with a material, where two different domain properties interact, and that's why when we describe, the mechanical domain characteristics, we have to specify that under certain electrical conditions. And similarly, when we are talking of electrical domain characteristics, we have to specify the mechanical conditions. And that's what we are calling as boundary conditions. So the electrical boundary conditions, what we looked at was when the material, when the transducer is open circuited, and then we call that condition as D equal to 0 because there's no displacement, there's no electrical displacement because no charges are flowing in or out of the material. So the hence D is equal to 0, and under this condition, if we apply a stress, both mechanical as well as electrical energy will be stored in the material. And under this condition, we say that the strain, capital S, is proportional to the stress with the proportionality constant, um, the compliance coefficient at constant D. And constant D means D equal to 0. D can be anything, but in this case, D equal to 0, right? So this is one condition we talked. And then this is the other condition we discussed, that when we actually short circuit, then the condition is E equal to 0, because why do we say the condition is E equal to 0? Because only mechanical energy will be stored and no electrical energy. Whatever electrical energy would have actually accumulated in terms of charge, because we are shorting the two terminals, we kind of ensure that there is no charge, no additional charges are getting accumulated. And essentially the electrical field inside the material, because of the external condition, that is 0. And under this condition, we said that if we were to measure the stress as a strain as a function of stress, the compliance coefficient, we will call it as S suffixed E. And the reason we'll call it as S suffixed E because it's at constant electric field at E equal to 0. So, and then we also discussed which one should be higher, SE or SD. So in this case, SE should be higher because when we look at the condition on the left-hand side, we have, I mean, the when we are stretching the material, we have both the mechanical property as well as the electrical characteristics opposing the change, right? So we will find that the condition given on the left-hand side, that is less compliant, or that is kind of stiffer, right, compared to what we have on the right-hand side. Or essentially, in other words, the right-hand side material will be more compliant. So SE will be higher. Similarly, we discussed the boundary conditions under, the mechanical boundary conditions. And we said that, look, if we apply a voltage as shown here, in this direction, the external voltage is opposite to the pulling direction, then the height of the transducer reduces, right? That also we discussed why it will reduce. And we have discussed it quite a few times to drive home the concept. And in this case, we are saying the stress is constant, T equal to 0. And we said that actually, even if there is strain, there is no stress. because we are letting the material settle into equilibrium, right? So there is no inherent material stress getting built in the material, even though there is strain, right? And under this scenario, we said that the permittivity, if we were to measure the permittivity, right, which will be given as epsilon T, then both mechanical as well as electrical energy is getting stored, right? And because we are measuring this at constant stress, and the stress is zero, we are denoting this by epsilon T, right, that we discussed. I posed a question also. I'll come back to that question that we asked yesterday. And then this is another condition we showed that, look, if we have the material, the transducer material glued to the wall, and we are not allowing the material to change the shape, right? And under this condition, if we apply a voltage, then we are saying that the strain is constant. S is equal to 0. And under this condition, if we were to measure the permittivity, we will denote that as epsilon S, right? And in this case, there is no mechanical energy is getting stored, right? Because we are not allowing the material to deform at all, right? And because lesser energy is getting stored, we said epsilon T will be higher because the energy that is getting stored is a function, is directly proportional to epsilon, right? So in this case also we have higher energy getting stored in the left hand side, and that is the reason we are saying epsilon T is higher. So going by that same discussion that we had yesterday, if we have, let's say, this material is lying on ground, this is not glue, and if we had a mass m sitting on it, right? So under this condition, if we measure the epsilon, that will also be epsilon T, right? Because it is under constant stress, right? And let's say we are denoting that as epsilon Tm for this example. And the one that we discussed, let's say that is epsilon T0. So now the question that we asked yesterday is which one will be higher? Is epsilon Tm going to be higher, or is it going to be lesser, right? Which is going to, so any one of you guys have thought about it, or you want to just quickly explain which one will be higher? You can kind of get a feel based on these two discussions that we did. Anyone want to?
Epsilon Tm will be higher.
So why do you say that, Nan?
Because when we put the mass, the more energy will be stored.
No, in fact, it is reverse, Nan. See, just think like this, right? When we put the mass, the delta L, right, that is going to see, right? Is it going to be more or is it going to be less?
More.
No, when you have a mass, right? When we have a mass, so in this case, you are saying it is more because you are thinking that there is already a material that is lying on it. That's the reason you are saying it is more, but it's not like that, right? Basically, what the weight does, right? Sitting on top, it is reducing the amount of freedom that the material will have to move, right? Just like in this condition, when we are glued, right? We are not allowing the material to deform, right? So the material M, when we are putting a weight on top of it, right? We are doing essentially, a similar thing, right? We are not allowing the material to move as freely as it would have, right? So basically the deformation that we will see when we have a weight on top of it, right? That deformation will actually be less. Basically what is happening is some of the energy that would have gotten stored in terms of mechanical energy is actually getting utilized to lift up or down this material, right? This mass that we have, right? So some of it is actually getting utilized for that. So the energy that is actually getting stored in the material in this case is lower, right? So basically this is wrong. So epsilon Tm will be lesser than epsilon T0. It's very similar to, to this, right? Whatever we have done on the left and right, right? It's the same stuff, right? Just that here we have glued, and in this case, instead of glued means we are ensuring that there is no strain at all. Here there will be strain, but the amount of strain will be actually lesser because we are kind of constraining the material to move, right? We are not allowing it to move as much. So the energy that is getting stored in the material will be lesser. Does it make sense?
Yes, sir.
Okay, cool. So now let's move on. So now we are going to look at, so we have introduced one form of the equation, right? If we go back, if we go back, we talked about, we derived this form of the equation and we called it strain charge, right? And why did we call it strain? Because we have the dependent variable for the actuator. Here we are talking of strain, and here D is the dielectric displacement, which is again nothing but, the charge density. So we talked of these this pair of equation, and whenever we are talking of the equations, we are going to talk in pairs. The same material will work as an actuator as well as a sensor, right? Because it's a transducer, right? It goes from one domain to another, electrical to mechanical and vice versa. So this is strain charge form, right? So this is one constitutive equation. And I had mentioned to you that time that there are other forms of the same equation, and we'll have a look at it. So now today is the time that we are going to have a look at that, right? So what we are going to do is we are going to look at all the forms of the constitutive equation, right? And we are going to denote the output and the input parameters on a table, right? So bear with me a little bit. So on one side, we are writing the mechanical, parameters, which is stress and strain, right? And remember, I mean, here on the gray side, I'm denoting this as the output parameters. Output parameter means the variable that is going to sit on the left hand side of the equation, right? Meaning these are going to be the dependent variables, right? So we have mechanical parameters, stress and strain, right? These are the two mechanical parameters we have, right? On the electrical parameters, on the output side, we have charge and voltage, right? That's pretty simple to understand. We have discussed this, right? Charge is nothing but capital D or polarization, right? Depending on in which context we are talking of, right? And voltage, of course, we know. So essentially, when you're talking of a capacitor, see, I mean, we have Q is equal to CV, right? We have only two things to talk about. We have in terms of electrical signals, right? It can be either the charge or it can be the voltage, right? So you have two output parameters in the electrical world, right? So we are going to talk about the electrical output parameters on this side. We're going to put it on this side, and similarly, and we are kind of well familiar of the notations that we are using so far, right? Strain, we use capital S. Stress, we use capital T. Charge is nothing but D. We are not using Q or something else for now, because Q we are reserved for something, some other purpose. And voltage, even though we are calling it voltage, but we are going to use the term voltage loosely here, because we are actually talking of the electric field E, right? Based on the equations that we are going to write, even though we are, in the equations we are going to write in terms of E, but when we are going to describe, we are going to talk in terms of voltage, right? Because typically, in common day-to-day usage, we don't talk about electric field, we talk about voltage, right? Which is essentially the same thing. It's just, voltage divided by the, distance, right? I mean, the electric field, right? The way we define it. And the input parameters also can be like this, right? It's the same stuff. So just output parameters sit on the left-hand side of the equation. Those are the dependent variables. But the same equation can be written in a different form, where the output parameters can sit actually on the right-hand side of the equation, right? And then we will say that, okay, we have strain and stress. And just note how I have, so I'll come to this. So, and also see the input parameters. Also, I have written as voltage and charge D. Same thing, but note how I am denoting it. So I have stress here and I have strain here. So what that means is if strain is an input parameter, right, then we will have stress on the output side, right? So basically if S is equal to S times small s times t, right? This is one way of writing it. Or we can write T is equal to Y times S. Y is the Young's modulus, right? Which is inverse of this guy, right? So basically the same equation. So here the strain is sitting on the left hand side, and here the stress T is sitting on the right hand side, right? So based on how we look at both the equations, we will have both the conditions, right? So when we, in this case, we can see strain we have written as an input parameter and stress is the output. Similarly here on this part of the table, we have told stress is my input parameter and strain is my output, right? And similarly, charge and voltage, right? I've used them interchangeably. Like in one scenario, this guy can be the input parameter and this guy will be the output parameter. In the other scenario, the charge can be the input parameter and the voltage can be the output parameter. So this is the way I'm denoting. So based on these possible combinations, we will have 4 pairs of equation, out of which one we have already seen. We have seen the strain charge form, right? So the first one, let's start with this. We have a stress charge form, right? So what it means, so please note this carefully. I'll go through this very slowly. It's very important to understand this set of equation. So what it means, what are the input parameters in this table that we have shown, right? What are the input parameters? S is an input parameter, right? Strain is an input parameter. E is the other input, electrical input parameter. So we have one mechanical input and one electrical input, right? And we will use a coefficient E such that the electrical and the mechanical parameters will be, so basically T and D, the output parameters is stress and charge. So we will write the equation such that the stress and charge is a function of strain and electric field, right? So this is one way of writing the equation, and this is called the stress charge form. Please note how we are talking about, how we are denoting the equation. First, we talk of the output, stress, right? This is on this side, and charge is nothing but the input side, right? So 1 second. Did I? No, sorry. So sorry, stress and charge. Sorry, no, so this is correct. So we have stress here T and charge is D, right? So basically stress charge form mean both the equation. So which one is the sensor equation and which one is the actuator equation out of these two? Can somebody quickly tell me? We will always talk, we discussed, right, that we will have the equations in pairs, one for sensor and one for actuator, or in other words, one will be the direct effect and the other will be the inverse effect. So out of these two equations, which one is the sensor? Which one is the sensor equation, guys, out of these two?
Second one is the sensor and first is actuator.
Great. So the first one is actuator because, as we discussed, the output from an actuator is mechanical. So the output variable T, which is sitting on the left hand side, which is the dependent variable. So this is the actuator, right? 1 second. You guys can hear me clearly, right? Or is there a problem with the voice or anything?
No, sir, we can hear you.
Okay, great, because it is giving a warning. But anyway, so the top equation is essentially the actuator equation, right? Sorry. So the top equation is essentially the actuator equation. And the bottom one is the sensor equation, because when we are talking of sensor, essentially we are talking of the output should be an electrical quantity. And this is what we have, right? So if you see, we are talking of stress charge form. So stress is actually denoting the actuator component output. Both are actually output components. One is denoting the actuator output, and the second one is denoting the sensor output, right? So if we look at this equation, so please look at this equation carefully again. So I'll erase this. So this is what we are calling as the stress charge form. So what we have, and we have associated a coefficient with this form of the equation, right? And that coefficient is nothing but E, right? So what we are saying is, what are the input parameters I have shown in this? One is strain, another is electric field E. Strain, input parameter, and electric field E, or voltage. I'm kind of going to use them reversibly, even though voltage and electric field is not the same, but we are going to use them interchangeably, right? So if we see here, to convert, so this first part, T is equal to CE times S, right? So the first part is nothing but the domain relationship, right? So CE is, so CE will be what? I mean, I've denoted, I'm calling this as CE, but essentially this will be what, guys? T is equal to CE times S. So T is nothing but Y times S, right? So Y is the Young's modulus. So instead of Young's modulus, I'm denoting this by C, right? CE. And why E? Because when we are talking of the domain property, right? When we are talking of the domain characteristics, we have to also mention the associated electrical characteristics. So C, so basically whatever is the transducer portion of the equation, in this case, the input variable is E, voltage E, right? So when we are talking of the coefficient associated with the domain, physical domain property, we have to hold the electrical environment to a constant, and hence we are going to say that C subscript E, suffix E, right, multiplied by S. So the first portion is the domain property, and the second one is of course the transducer property, right? So this is E times, it's the transpose. Please hold on, why it is transpose, I will discuss this. This is important to note why it is transpose. But for now, let's assume it's E times, small e times capital E, the voltage, right? So this is how we have written the actuator equation. So let's look at the sensor equation. So D is E times S and epsilon S times E. So which one is the domain property? The domain property is this guy, right? Because the output is also electrical, and when the input is also electrical, both the components are in the same domain. So we are saying as domain property. So the domain property is related in the electrical domain. The domain property is related by permittivity. And whenever we are talking of the domain property in the electrical domain, we have to specify what is the mechanical environment, what is the mechanical condition, right? And because we have to specify what is the mechanical condition, we are going to denote permittivity with a subscript S, right? Epsilon S, meaning for a given condition of strain, what is the permittivity? So we are going to denote that as epsilon times S. And E times S is nothing but the transducer portion of the equation. So this form is called as the stress charge form. And the reason why we are discussing this, it is very important to understand. So if some of you, as I said, right, go on to work for sensor design companies, and there are quite a few of them extremely famous. And if you look at the data sheet, right, of piezoelectric material, you will find all these coefficients. And by the way, this is not there in textbooks. Even the explanation and all that, you will not find this in textbooks. But it's important to understand the modern concept of how the things are kind of denoted and why, right? So this is one form of the equation. So any questions here. I think the only question that I've left unanswered is why we are using a transpose here. It's essentially these are all matrix, and we are going to see the matrix form of the equation. But for now, just hold on to the thought that why it is a transpose. But rest of the equations, is it clear what we are trying to show and why? Any doubt from anyone? No doubts?
Sir, I have a doubt.
Yes, go ahead.
Like
Go ahead.
in this equation, this E and in previously which we studied, there was a constant D. So, sir, is it constant in all the cases because we are not attaching any subscripts to it, like in
No.
certain conditions when strain is 0?
Yes, yes. No, so please, so that's a good question. So again, let's look at it. Why there is no D coming here, or even why just D, right? We also are not showing here. So here, what are the two boundary conditions we talked about, right? We talked about S with the constant. What are the two things that we talked? One was we talked about the compliance coefficient with S is equal to, S subscript E or S subscript D, right? We talked about that, right? Right? Here we are showing C. C is nothing but the inverse of S, right? But we are showing only E here, not D. That's your question, right, Shubham? Why only one subscript is coming, not the other one, right? That's what, is that your question?
Yes, sir.
Okay. So the answer to that question is, if you carefully observe, is what are the input parameters? What are the independent variables, right? Meaning what are the variables, right? I'm giving independently from the environment, and that is S and E. So these are the two guys. If you are doing an experiment, these are the two guys which are in your control. These are the environmental variables, right? Or you can say this is not under the control of the output, meaning the output is decided based on strain and electrical field, right? So these are the two things which we are controlling, and these are the output parameters. So when we are talking, when we are writing the equation, the environmental parameter must be referred to. Here, D is not even an environmental parameter. D is an output, right? So the environmental parameters, the input side, on the input side, we have only E and S. And that is the reason when we are talking of the coefficients, we will talk about only E and S, because that is what is my input environment. I'm not talking of D at all. D is what I'm going to expect as an output. So D is not under my control. D is decided based on E and S. Does that make sense?
Yes, sir. That part I understood. My question was that with this constant E, and in previous case we have small d constant. So why don't they have subscripts? Like they are actually constants or?
Oh, okay. Why don't they have subscripts? Okay. So the reason why, okay, so you're talking of these red guys, is it? Why these guys don't have subscript, right?
Yes, sir.
So why they don't have subscript? Because so T is equal to, so this is what is the transducer coefficient. So the transducer coefficient, right? It is going, so if you see, right, in both cases, T is mechanical and this E is electrical, right? So basically you are moving from one domain to other. So when you are moving from one domain to other, there is no, you are already moving from one domain to other. There is no concept of keeping one thing constant, right? So because it's a transducer coefficient, the transducer coefficients will never have subscript. D was also a transducer coefficient. The coefficient D helped us relate the mechanical domain with the electrical and vice versa, right? So there you cannot say that, okay, one of them is constant, because if you make one of them constant, then essentially both of them are constants, right? Right?
Yes, sir. Yes, sir. I got it.
You got it, right? So that is the reason why there is no subscript for the transducer coefficient. And please note, in the table that I have shown, please note, for this form of the equation, right? I am actually only talking about the transducer coefficient. So basically, the input parameter, which is strain and voltage, electric field E, is converted into the output parameter stress and displacement, the dielectric displacement or the charge density. Though these two have been converted using one single coefficient E, and this is the transducer coefficient. So these guys are the transducer coefficient. Using these coefficients, we will be able to move from one domain to other, because that's the bridge. From mechanical to electrical, this coefficient is the bridge. And when we are talking of the domain coefficients, when we are talking of CE is a mechanical domain coefficient. And similarly, epsilon S is an electrical domain coefficient. When we are going to talk about that, in these coefficients will be talked about by holding the other domain constant, right? Because it's the same domain. I think this is clear now, right? It's very important. I'll spend time here because there will be, and trust me, there will be questions. I'll give you assignments also, you will see, and there will be questions on this in the exam. It's very important to, and again, as I said, what is not important, few years down the line, you'll probably not even remember the equations, right? But so why are you even learning it, right? We are learning, number one, because many of you, or some of you, not many, some of you might actually end up dealing with these equations in the industry, and which is for sure you will deal with it. And number two is to learn the approach. And no matter where you are, right, you will see similar kind of problem statements coming when you are talking of two domains talking to each other, right? So the key takeaway will also be the approach, right? So these are the two key reasons. But at the same time, our goal will be to remember the equation by understanding it, not by kind of mugging it up, right? And we have explained, how these equations are formed. So one is a domain property, and the other is a transducer equation, and we are kind of adding them together to ensure that we get the final output. Is there any other thing that is striking to you in this equation other than the transpose? Any other thing that is striking in this pair of equation?
The negative sign.
Exactly, the negative sign. So we are going to talk about that also a little later, and probably once we understand why it is negative, then we will realize. So basically, the coefficient E is related in a way that, the stress. So basically, you can say that this guy and this guy will work in opposition to each other because of the transducer equation. The coefficient, the electrical domain is going to work in opposition to each other. So if somebody makes E negative, then this negative would become positive, but then here we will have a negative, right? Somebody can absorb the negative sign here inside this E, but then this guy will become negative, right? So there will be always in this form of the equation, there is these two guys are going to work in opposition to each other. So physically also we can talk about it, but let's move on and look at the other portions of the, other forms of writing the equation, right? But good observation, Shubham. So the second form is similarly the strain charge form. And again, why we are calling it strain? Because we have two equations, right? The output in one we have strain and the other output is D, charge. So that's the reason we are calling it strain charge form, right? Stress charge, this is strain charge. And when we are talking, and this is what we had seen earlier, right? And I think this is what even Shubham was alluding to, that, sir, why even in D we didn't have a subscript. We always have a subscript in the other cases, right? And then I said that, why we don't have a subscript here, because this is anyway the transducer coefficient. This is the bridge. When you are talking of the bridge, the river must flow. we cannot hold, right? We cannot say that, hey, you don't, I mean, we can't say the water not to flow and then talk about the bridge, right? The bridge is the bridge. Whereas when we are talking of a domain relationship, like this is S equal to, compliance times the stress, strain is equal to compliance times the strain. Under this condition, we are going to talk about the other environment. So this guy is again an input parameter or an input environment variable. This guy appears here, right? This guy appears here. And similarly, when we are talking of displacement D here, right? So epsilon T comes here. So basically this guy comes here. T comes here, right? So this we have already talked about. So this is the second form of the equation, and this is the most commonly used form of the equations. When you are talking of data sheets of piezoelectric materials, this is what you will see mostly being talked about. There are other forms, right? And by the way, if few of you actually want to pursue higher studies, PhD in sensors, and this is extremely an interesting domain. And my own PhD was in this domain of developing electronics around sensors, right? I mean, I'm an analog electronics guy, but so if we are to, develop electronics, then of course we will need to understand the physics of the sensors. So this equation is the most commonly used set. So the third form is what we call as stress voltage form. And that again is very clear, right? Why it is stress voltage. So essentially you can understand, right, how the equations are evolving, right? We actually have, in the mechanical world, we have two variables, stress and strain. And in the electrical world, we have two variables, charge and voltage, right? Now we are taking the possible combinations of these input parameters and output parameters and saying that, okay, these are my different coefficients, right? So when we are moving from, the strain and charge, right? I mean, this is strain and charge. When we are moving from stress and voltage to strain and charge, so the coefficient that is associated from this movement for this movement is D, right? In the third, which is nothing but stress and voltage form, again, the same stuff, right? T is equal to CD times S. So C is nothing but you can say the same as Young's modulus, right? And here, whereas E was constant, in this case, D is constant. So this guy comes to the subscript here, right? Because these are my input environment variables, right? S strain is my input environment variable and D is my input environment variable. So when we are talking of the domain relationship, we are holding the other environment variable as a constant, and that's why we are talking of CD, right? And then E is again this, right? So this is at this inverse, I think you can understand, right? Permittivity times inverse of that, right? This you can understand, this is the electrical domain relationship, right? So Q equal to CV. So in this case, if E is V, right? So we have Q is equal to CV and Q is nothing but, let's say, D. And we have C and V is nothing but, let's say, epsilon times, C times E, right? So basically when we are talking of, and C is nothing but what? So implies this is epsilon A D times E, right? So why is this epsilon inverse? So if you see here, if I write E in the form of D, right? So it will be epsilon inverse, blah, blah, blah. I mean, some constant will come and then we have D. So that's why this inverse is coming, right? That's why this inverse is coming, right? And Q is again the bridge coefficient, the transducer coefficient. And in this case, again, we see both are negative signs. So this we can talk about a little bit, or even we can derive, but this is how it is, right? We cannot, discuss, some of it has to be, you have to probably read some material. You'll not find this in a textbook anyway, so straightforward. So this is the stress and the voltage form, right? So now we are going to talk about the last form, which is this. So in the last form is nothing but strain voltage, right? Again, the same stuff. We have strain and voltage, the output form S and E, and we have coefficients G associated with it, right? And here also the same stuff, epsilon T, this guy comes here and this guy comes here, right? And this is what, so these are the four different forms of the equation, right? So anything that comes to your mind, you know, when you see these four different forms and we have, you know, brought in four coefficients, E, D, Q, and G. Any natural question that comes to your mind about these four coefficients? Any natural question that, you know, sir, you have talked about four coefficients, but we are talking of the same material, right? Just that we are writing the equation in different forms, right? So then what will be the next obvious question that can come? Anyone?
Their
That the four
relationship.
coefficients will be interrelated.
Exactly. The four coefficients, excellent. The four coefficients will be interrelated, right? So so we have to relate these four coefficients, and the relationship can be we can move. So how many? So we have four different forms of the equation. So how many kind of movement can be? I mean, each set of equation can be moved to the other set, right? So how many possible combinations will be there? 6 different combinations, right? So if you see, someone can move from this form of the equation to this form, like E to D can be one, someone, and vice versa, of course. And somebody can move from D to G, right? From here to here. Somebody can move from here to here, and somebody can move from here to here, right? And we can also move in this direction and this direction, from this set of equations to this, right? Right? So total, how many different conversions we can have? 6, right? 1, 2, 3, 4, 5, and 6, right? That is clear, right? We can convert, we can have 6 different, types, I mean, 6 different ways to convert, right? From, one equation, I mean, one variable to the other, right? That is clear. That should be obvious, right? Okay. So, we'll, have a quick recap of whatever we discussed so far. Or maybe we will stop after a few more minutes. So materials which does not have a center symmetry exhibits piezoelectric characteristics, right? Meaning the center symmetry is disturbed the moment we apply a force. The center symmetry is disturbed, right? And that results in a net effective dipole, and because of which, so this we discussed, right? And another key point is it's present in both crystalline and non-crystalline material, right? It can be shown in both, types of material, and it can be harnessed in dielectric material because the displaced charges need to be made available across the two surfaces, right? And that is the reason we talked about having two different plates on the quartz crystal, right? That to harness the charge, quartz is actually a silicon dioxide, and that is not a good conductor actually it's a dielectric material. So to work with the charges, we must have two electrodes associated with it, right? And also this is so this equation is a domain equation wherein we are not talking of everything is electrical, right? We have we have E is also electrical, P polarization is also electrical, and D is the net displacement, right? But what this is showing is polarization is because of an external thing that we do, whereas E D and E can be directly related because of, let's say, some inherent charge that is there, right? And also we talked about polarization in simple terms, D times sigma, right? And instead of sigma, we are not using the symbol sigma to denote the same equation. We are using T, right? So this is one thing that we saw. And then the thing that we have to understand, what is the piezoelectric behavior, this polarization, right? What sort of a component is that? Is it a vector? Is it a tensor? Or is it a scalar? Right? That we have to, because then our maths are going to become more and more involved, right? So if we talk of stress, right? So when we talk of stress sigma or T, right? That is nothing but force divided by area, right? Force we know is a vector, right? And area is also a vector, right? That we understand, right? Any doubts on that? Why area is also a vector? Area is also a vector because if we are talking of, let's say, this particular face of a cube, right? The direction normal to it is the vector direction of the area, right? So basically, when we are talking of sigma, we have two vectors associated with it, right? So this force vector can have how many directions associated with this force vector? How many directions we can have, guys, on the force vector? So total number of directions we can have is, of course, X, Y, Z, right? And then we can have, I think probably we'll stop here because we are going to look a little bit more in terms of the matrix equation and how the matrix is formed based on these properties, and we have to understand why it is a tensor and what is the dimension of the tensor. 3 cross 3. We'll have to, I think we covered an important topic today, so probably we'll take a break today. And guys, today we have a lab, and please ensure that you join the lab. Today is going to be our first session, and I've made for lab, attendance will be mandatory because you will have to present, and I will set the context today in today's class how we are going to do the labs, and we are going to make them interesting, and more than interesting, we should learn something from the lab sessions, right? So see you in the all of you guys will be in the lab session, right? I mean, the same class will be in the lab session, right? Anyone? Same class, right? The same set of people, I believe, right?
Yes.
Okay, cool. So yeah, let's meet at 2 o'clock then, and then we'll take it from there. Have a good day, guys.
Thank you.
Yeah, thank you. Bye.